Hello friends, so far in this course on radiative heat transfer, we have learned about the radiative characteristics of plane surfaces and we have also learned about the view factor. Now in this lecture we will combine the knowledge of view factors and radiative characteristic of surfaces to solve the radiative heat transfer problem between black surfaces. So we will be studying the radiative heat transfer inside an enclosure. So there can be an arbitrary enclosure, okay, and the surfaces of this enclosure will be assumed to be black. Initially we will assume that the temperature along the surface is not uniform, that means the temperature depends on the location R, and we assume that the surfaces are black. So by assuming that the surfaces are black, we are basically removing the possibility of reflection from the surfaces. So the reflectivity or reflectance of the surface will be equal to 0, and these surfaces will be acting as perfect absorber and perfect emitter. So epsilon and alpha will be equal to 1. We have also assumed the surfaces to be black because we want to make sure that alpha and epsilon do not depend on wavelength. Although these relations are equally valid for gray surfaces also, we will see. So we assume that the surfaces are black, they are perfect emitter and absorbers. There is no participating medium, so the medium inside this enclosure is vacuum, there is no participating media. We will extend this method to participating media where the enclosure is filled with some kind of gas, okay. And the third condition is the surfaces are diffuse, that means they emit radiation uniformly in all directions. So they are diffuse emitter, okay. Such surfaces are, although we may think that these surfaces are lot of restriction is there on the black surfaces, but still there are practical problems such as boilers and furnace, where we have the walls covered with the small carbon particles called soot. And in radiation characteristics of surfaces, we have seen that the soot basically essentially acts like a black body. So the walls covered with soot of these furnaces can be approximated as black surfaces. So we basically are going to find out the relation between these surfaces. So here I am just going to take a special enclosure where we have small opening through which some kind of radiation from outside can also come, okay. There is a small opening inside this enclosure and there is a small elemental area, let us call this dA, okay. So we want to write energy balance for this surface dA, okay. So surface dA receives some radiation from rest of the enclosure as well as the outside radiation, okay, H0. H0 is radiation coming from outside the enclosure. So the radiation received by surface dA will have two components: radiation received from the enclosure itself and radiation coming from outside, that is H0, okay. In together with the radiation received by surface dA, the surface dA will also emit some radiation. So this radiation emitted by the surface, let us call this, write it as EBI, okay, or write this small area as DAI, okay. So the total amount of energy transferred or exchanged by surface dAi includes the energy emitted. So this is the energy emitted and this is energy absorbed, okay. There is no alpha because alpha is equal to 1. So energy emitted, which is same as the black body because we are considering black body in this case, and it is a function of R because we have assumed that the temperature varies with surface, okay. So the emissivity or emittance of the surface will also vary with surface location because the temperature varies with location. So the emittance or emitted energy is simply the black body emissive power as a function of R or as a function of temperature, and then energy absorbed. So this energy absorbed is basically alpha times energy received, alpha is equal to 1. So basically it is equal to energy received. Now energy received Hi is basically sum of the energy emitted by the entire enclosure. So we can write it in integral forms, okay. The energy received by the surface is equal to energy emitted by the enclosure at any location integrated over this area dA prime. So we have some area, let us call this dA prime. Okay. So, energy emitted anywhere on this enclosure times the view factor dF dA prime to dA. So, we have to look at the view factor between these two areas. Okay. Energy emitted by this surface times the view factor times the emission power integrated over the entire area of the enclosure plus outside radiation H naught falling on this area dAi. So, that is the total amount of energy received at surface dA. Okay. So, using the reciprocity theorem, so what we have is here the view factor dF between small element area dA prime and dA, and then the area multiplied by dA prime. Okay. So, we can write this as, so we can, I will just write it down here, dF times dA prime to dA times dA prime is equal to dF dA to dA prime times dA. Okay. So, using the reciprocity theorem that we have substituted here. Now, cancelling out the dA term on the both hand side, what we get is the total amount of irradiation on surface dA. Okay. So, we have just removed the dA from the both hand sides. So, total energy radiated by on the surface dA or energy absorbed by the surface dA is simply equal to integral EB r prime, that is emission power of the black body at any location times the view factor between the two surfaces plus outside irradiation. This is outside irradiation. Okay. Now, substituting this value of HR in this equation, we get radiative heat flux at any location. So, we have this enclosure, this is surface dA. Okay. So, the heat flux here Q is equal to emission power at this location minus total irradiation from all the surfaces of the enclosure and outside irradiation. So, this is basically the expression for heat flux on a black enclosure at any location R. So, heat flux at any location R depends on the amount of energy emitted from that location minus total amount of energy received at that location from the entire enclosure and outside irradiation. Now, what we will do is, now this type of problem cannot be solved. Okay. We have to do some kind of simplification to solve this integral. Okay. And what kind of simplification we can do is, first we will approximate this enclosure using some plane surfaces. So, we will fit some plane surfaces inside this enclosure to make this problem solvable. Okay. There can be n number of surfaces. Okay. So, we have to basically do some kind of approximation. We have to approximate that the enclosure contains some n number of surfaces and each surface has uniform temperature distribution. So, there is uniform temperature on the surface. Okay. There is no variation of temperature on that particular surface. From one surface to another the temperature may change, but on a particular surface the temperature is constant or uniform. Okay. So, by doing this, EB term can be taken out of the integration. Okay. Now, the temperature is uniform on a surface. So, it does not depend on the area of that particular surface. So, it can be pulled out of the integral, but it will be in the integration. Summation. So, we have divided the enclosure into n number of surfaces. So, summation 1 to j is equal to 1 to n, j is equal to 1 to n, EBJ, the MSC power of jth black surfaces, and then in the integration we are just left with this view factor minus the outside irradiation. This is outside irradiation. Okay. Now, looking at the term in the integral, what we have is basically dF, the view factor between small element ai and small element daj, and we are basically integrating over the entire enclosure. Okay. We have to integrate over the entire enclosure. So, this can be represented as the view factor dij, that means view factor of a small element dAi or any location of the enclosure with the entire enclosure. So, Fdij represents the view factor of any location of the enclosure with the entire enclosure, okay. And we have eliminated the integration from this equation. So, all we are left with is heat flux at any surface Qi, okay. Now, we are still using the dependence on Ri, okay, because view factor does depend on location. So, the view factor of this location on this particular surface is different from view factor of this location for the same two surfaces, okay. The view factor between these two and these two is different, and that is why the heat flux will vary along the surface. So, although the temperature is uniform, we have assumed that the temperature does not vary from one surface to another, but the view factor does vary. The view factor is not uniform over the surface. So, view factor is changing over the surface, and that is why the heat flux is going to change. That is why we have put that the heat flux on surface I at a location Ri, okay, it is going to be different at different locations, is equal to emissive power of the surface I, because the temperature is uniform, it does not depend on R, minus summation over the all the surfaces, okay. Ebj is the summation over all the surfaces, and the view factor from all the surfaces to that small element di. So, Fdij is the view factor between small element dai and all the surfaces of the enclosure, and this is going to change with Ri minus the irradiation from outside, okay. Now, so again although this we have already simplified this problem by assuming that the enclosure can be represented by a finite number of surfaces, but still there is a problem in finding the view factors Fdij. So, we have to do again some simplification. So, what we will do is we have heat flux varying along the surface, that is Qi varying with the location on that particular surface I. We will try to find out average heat flux, average radiative heat flux. So, what we do is we integrate over the area dAi. So, Qi Ri is a heat flux at a particular location integrated over the entire area dAi and then divided by Ai. So, this is going to be now average heat flux. So, Q1 is average heat flux, Q2 is average heat flux, it is not a location wise heat flux, it is average heat flux over the entire surface of the surface I or j. So, now we just substitute the value of Qi Ri in this expression. So, Ebi does not depend on the surface area Ai. So, Ebi is taken out, minus j is equal to 1 to n Ebj Fij. Now, Fij is finite area view factor. So, we define Fij as Ai Fij is equal to integral over the entire area dAi Fdi to j, okay. So, this is the expression that we will use in solving our problems, okay. So, our final expression is Qi, that is heat flux on surface I, is equal to emissive power of surface I minus summation j is equal to 1 to n emissive power of surface j and the view factor between I and j. So, this is the heat transfer between surfaces minus the outside irradiation at surface I, okay. So, H naught I is the outside radiation. So, this is the first form of the energy balance between black surfaces, okay. We have another form of the same equation. What we do is we write Ebi is equal to summation j is equal to 1 to n Ebi Fij, because summation j is equal to 1 to n Fij is equal to unity, multiplying both sides by Ebi, we get j is equal to 1 to n Ebi Fij is equal to Ebi. So, if we write this in this form and substitute for Ebi in this equation here, we get Qi is equal to summation j is equal to 1 to n Fij Ebi minus Ej. Now, we have the relation, the same relation we have written in another form in terms of difference in emittance, black body emissive power of the surfaces and then summing over. So, we have this difference in emissive power, black body emissive power. Okay, so, so this is another form. Sometimes this form is preferred, sometimes the other form is preferred. Okay. So, let us do one problem to understand this method. Now, in this method we have taken a small furnace. Okay. The furnace basically is cylindrical in structure. The bottom surface A1 is electrically heated using some coils, okay, and it is maintained at a temperature of 1500 Kelvin. Okay. The cylindrical sides of this furnace are insulated, that means the heat flux through these walls is 0. Okay. Let us call this surface 1, the cylindrical surface is 2, it is insulated. So, Q2 is equal to 0, and the top surface is exposed to the environment in such a way that the temperature at this surface is uniformly maintained at 500 Kelvin. So, we have to find out how much heating we have to provide to this electric heater at this surface. In other words, we have to find out Q1, because the amount of energy in the electric heater is basically the heat flux, and we have to find out the temperature T2. Okay. So, these are the two quantities that we have to find out. So, we will use the theory of black body enclosure that we have derived to solve this problem. So, let us write down the solution of this problem. Okay. So, we will use this expression. So, let us first write down this expression. So, we are going to use this expression Qi is equal to Ebi minus, so Qi is equal to Ebi minus summation j is equal to 1 to n Ebj Fij, okay, minus H naught I. Okay. So, there is no outside irradiation, so this quantity will be 0. Okay. So, we will have I is equal to 1, 2 and 3, okay, where I is equal to 1 means the bottom surface, 2 is the cylindrical surface and 3 is the top surface. Okay. So, Q1 is equal to Eb1 minus Eb2 F12 minus Eb3 F13. Okay. Let us call this equation 1. Now, Q2 is equal to Eb2 minus Eb1 F21 minus Eb2 F22. So, please note there is a term for F22 here, because the cylindrical surface, whatever it emits, although some part of it will be received by bottom and top surface, but some part of the emission from the cylindrical surface will fall onto itself. Okay. So, there is a term for F22 here, there is no term for F11 because they are flat surfaces. So, no radiation emitted from surface 1 and 3 will actually fall onto themselves. So, then we have Eb3 F23, okay, and this is going to be equal to 0. Okay. So, from this, let us call this equation 2. So, from equation 2 we can solve for Eb2, because Eb1, Eb3 are known. All the view factors we can look at these view factors from the book. These are standard configuration. We have already learned many methods to calculate the view factors. So, Eb1 can be written in terms of view factors and the emissive power as Eb1 F21 plus Eb3 F23 1 minus F22. Okay. Now, we can simplify this relation a little bit from summation rule. F21 plus F22 plus F23 is equal to 1. So, 1 minus F22 is equal to F21 plus F22. Now, what is F21 and F22? Sorry, F21 and F23. F21 is the view factor between cylindrical surface and the bottom surface, and F23 is view factor between cylindrical surface and top surface, which are equal. So, F21 is equal to F23. So, with this we get Eb1 or Eb2, this is Eb2 is equal to half Eb1 plus Eb3. Okay. So, we have taken this out. Okay. So, Eb2 is equal to half Eb1 plus Eb3. Okay. So, now Eb1 and Eb3 we already know. So, we can solve for this. Okay. So, sigma T to the power 4 is equal to half sigma T1 to the power 4 plus sigma T3 power 4, sigma will cancel out, and from this we can get T2 is equal to 1265 Kelvin. Okay. So, the temperature of the surface 2, that is the cylindrical surface, is 1265 Kelvin. Okay. Now, to find out the heating requirement, that is amount of energy we have to supply to the electric heater, so that the bottom surface can be maintained at a temperature of 1500 Kelvin, will be equal to Q1 times the surface area A1 times Q1, and this will be equal to pi r square. Okay. The radius of the cylinder is already given. Okay. The diameter is given as 10 centimeter. So, r in this case is 5 centimeter or 0.05 meters. So, r we know, and then Q1 from this expression is equal to EB1 minus EB2 F12 minus EB3 F13. Okay. So, EB1 we know, so this will be equal to pi r square sigma T1 power 4, T1 we know is 1500 Kelvin minus T2 the power 4, T2 we have already found, F12 minus T3 power 4 F13. Okay. Now, all these U factors we can calculate using the table in the book. I will just give you the value here. So, F13, that is parallel disc F13, the U factor is equal to 0.0557, and F12, that is between disc and the cylindrical surface, is equal to 0.9443, and with these values we can substitute in the relation. We get Q1 is equal to 1.175 kilowatt. Okay. So, the total amount of energy that is required from the electric heater is 1.175 kilowatt. Okay. So, this is a simple example on the radiative heat transfer between black surfaces. Okay. We will do one more problem. Okay. Now, in this case the problem also considers the radiation from outside, that is we have radiation coming from outside the enclosure. So, we have basically a rectangular right angled groove. So, there is a 90-degree angle. Okay. We have two surfaces, they have infinite width in the plane of the board. Okay. So, the surfaces have basically an area A1 is equal to A2 is equal to A, assuming unit depth in the plane of the board. The angle between the two surfaces is 90 degree. Okay. Now, radiation on this enclosure or groove is basically the solar radiation at an angle alpha as shown. The temperature of the enclosure is maintained. So, it is an isothermal groove, and the temperature is kept as T. So, we have to determine the net radiative heat transfer from the groove. That means, we have to find out total amount of heat transfer rate due to radiation. That means, the area of the groove times Q1 plus Q2. So, this is the quantity that we have to find out. Okay. So, this will be simply equal to A, because area is A Q1 plus Q2. So, this quantity we have to find out. So, let us solve this problem. This problem is again a very simple problem. So, we will use this expression Qi is equal to Ebi minus summation j is equal to 1 to n Ebj Fij minus H naught I. Okay. So, this H naught I is irradiation from outside the enclosure. Okay. So, H naught I is the irradiation outside the enclosure. Okay. So, we write for surface 1 Q1 is equal to EB1 minus F122. Now, there is no F11 and F22 because these are flat surfaces. So, F12 EB2 minus H naught 1 and Q2 is equal to EB2 minus F21 EB1 minus H naught 2, where H naught 1 and H naught 2 are basically the radiation falling onto this surface from outside. So, H naught 1 is equal to Q solar. Okay. Q solar is the solar energy coming onto the surface at an angle alpha 1. So, H naught 1 is Q solar cos alpha and H naught 2 is equal to Q solar sin alpha. Okay. So, one plate makes an angle alpha and another surface will make an angle 90 minus alpha. So, so what do we get? And the view factor F12 is equal to F21 because of symmetry, and we can find out again using tables. So, there is a entry in the view factor table in the book for 90-degree grooves. Okay. And this fact F12 and F21 is simply equal to 0.293. Okay. If you calculate using the tables, the view factor F12 and F21 you will get 0.293. Okay. Now, so all the quantities we know, EB1 and EB2 we know they are same, sigma T to the power 4, the temperature of the two plates is same, and F12 and F21 are also same. Okay. So, what do we get? Q1 is equal to, let us just write it as EB minus F12 EB minus Q solar cos alpha, and Q2 is equal to EB 1 minus F12 because F12 and F21 are same, EB minus Q solar sin alpha. Okay. Now, the total energy, total irradiation or total radiation exchange from the groove is equal to A times Q1 plus Q2. Okay. So, this will become equal to A times, and this will be equal to 2 times A EB 1 minus F12 minus cos alpha plus sin alpha. Okay. So, this becomes Q is equal to 2 times the area A sigma T to the power 4, T is the temperature of the groove, 1 minus 0.293 minus Q solar cos alpha plus sin alpha. Okay. So, this is how you can incorporate the irradiation from outside the enclosure into your problem. Okay. So, in this lecture we developed relation for radiative heat transfer, radiative heat exchange between black surfaces in an enclosure together with irradiation from outside the enclosure. In the next lecture we will consider radiation exchange between grey surfaces. Thank you very much.